Hello everyone, welcome back to another Geostats lecture video. And in this lecture video, I want to continue our discussion on going through an example regression setup. So in the previous video, we set up all of our data and we examined the EDA. And full disclosure, right, this is not a perfect example of a model, but again, we're just going through the steps so that you understand where different pieces are coming from. So the next step, once we've figured out our autocorrelation, figured out our normalities and all those kinds of things, and we've talked about that. The next thing is going to be to generate a regular regression, and we're going to use this regular regression in terms of something called the Lagrange multiplier. So first of all, let's go ahead and set up our ordinary least squares regression, and again, this is going to be a review. It takes in a formula, which in our case is going to relate the smoking to the, sorry, get it backwards. It's going to be relating the cancer rate, or it's going to regress CNCR underscore rate against our variable smoking. Okay. It also requires the data, and the data is going to be our pen underscore UTM at data. Okay, so if we run this, we're going to our first simple linear regression, which we can use summary of OLS to get a feel for what the model did. Okay, and again, I am not justifying that this model makes sense. I'm just simply saying this is our example. So if we look up here again, just to quickly go through what the summary shows us for regular regression, right? This is telling us what we did. This is telling us our coefficients and whether or not they are significant. And then down here we have our R squared. So you can see this is another example, right? 0.05. So we're explaining 5% of the variation, and it's marginally significant, right? So this is not a very good model at all. Okay. But what we can do is we can use this ordinary least squares regression model with something called a Lagrange multiplier. So Lagrange multipliers are basically a statistical way to examine whether or not a given set of variables will be improved in terms of model performance if we incorporate either the spatial lag or the spatial error model. Now, we're not going to talk about the spatial error model. That's going to be next week's module. But so we're sort of, jumping ahead a little bit here. But the Lagrange multiplier is a great way of sort of statistically checking whether or not you should run a spatial model. And the way this works is we use a function called lm.test. May have had a typo. There we go. Sorry. lm.capital LM tests from the SPDEP package. So again, right, this basically gives you tests for the 5 different models. Now the models that it works with are, if you went on tests, right, LAG-MER, which is the error model, LAG, which is the spatial lag models, and then we have the robust versions, and then we have the SARMA. Now, we don't need to worry about SARMA. We're not going to talk about SARMA at all in this class. But what we do have are LM-MER, LM-LAG, RLM-MER, and RLM-LAG. So if we go ahead and just quickly run through what the code requires, right, it requires a model. So this is going to be our OLS model that we just created, and it requires a spatial weights matrix. Right? That's what this list W is. So we're going to go ahead and run that code. So let's call it from the package. SPDEP : LM tests. Right, it requires a model. So this is a generic least squares regression model. It requires a list W, which again, this is going to be our pen underscore spatial weights matrix. And then for tests, we're going to run all. So this is going to test for both the spatial error, which we aren't talking about now, spatial lag, which we are talking about, and then something called a SARMA model, which we're not going to talk about at all in this course. So if we run that really quickly, you'll see that what we get, let me pull this up just a little bit so we can look at it all at the same time. So what we get, this is just telling us what we've already run. So this is a recap of the model and the weights. So breaking this down, LMER is the Lagrange multiplier for the error model. LM-lag is the Lagrange multiplier for the spatial lag model. What you're going to want to do is you're going to want to look at these. You're not necessarily going to need to interpret this, the multiplier coefficient here, but you do want to kind of look at the p-value. And if one of them is statistically significant, great. That's an indication that you should perform either the error model or the lag model. If they're both significant, right, then you need to go down to the robust, or the RLM, the robust Lagrange multiplier. And basically what this does is this accounts for some of the things that can artificially affect the p-value up here. And so if they're both significant, you want to look down here, and you want to take whichever one of these has the lower p-value. So hopefully that makes sense. If one of these is significant, great, you're good. If they're both significant, go down here and take whichever one has the lower p-value. Okay? And then we can largely ignore SARMA. Okay? So that's how the Lagrange multiplier works. So in this case, unfortunately, as I said, this isn't a really great model choice, but you can see that we actually wouldn't need to do any spatial modeling, but we're going to anyway. So again, in this video, I just wanted to introduce this idea of the recap of a linear model and then using this Lagrange multiplier test to test whether or not we should approach from a particular type of spatial model. Hopefully that makes sense, and if you have any questions, please reach out. Thank you.